All right, let's do an example from the workbook of a series problem. Oh, and I'm messing up. Hang on one sec. All right, I'm hoping you can all hear me now. So anyway, we're going to do a couple problems out of the workbook for series problems. And we have one here where we are given 100 volts. We only have two resistors. It's nice and simple. And we have a current in resistor 1 of 0.15 amps. We would never put that down as an answer, though. We would always say that it's 150 milliamps. And we have 18 ohms in resistor 2. So we have a couple of pieces of information. And one thing we always look for in a series problem is the current. So we know the current is constant, so we're going to take that and put it everywhere else also. So now we have a current here and we have a current here, and we can find out lots of things, right? One of the things I like about this problem is it reminds you, now we could solve this with this all by itself, but I want you to look at this. We have a voltage here, we're missing the voltage here, well, we're missing the voltage in both. I'm thinking of a different problem then, sorry. Okay, well, when you're looking at a series problem, remember that the voltage drops have to add up to the voltage supplied. If we were given a voltage in one of these, we can subtract that from the supplied voltage and find the, let's say we had 3 given voltages and 3 resistors, and we were missing the 4th voltage, and we had a supplied voltage. We can subtract the existing resistor voltage drops from the total voltage drop and find our voltage drop across that one resistor. But this is not the problem I was looking at that had that in it, I guess, but that's okay too. So let's just do some dividing. Now remember, if you write it P-E-I-R, if you're going down, you know you can divide. So 100 divided by 0.5 is what? No, I don't think it's 200.
666.
Say again?
666.
666.66? 0.66. In other words, it's continuous, which means it's 666 and 2/3. Okay, that's good. Now let's multiply up and find our power. How much power do we have? Is it 1.5 watts?
Voltage times current.
Voltage times current is apparent power, by the way. But in this case, it's true power also, because it's pure DC power and pure resistance, as pure as resistance gets anyway. So 100 times 0.15 is what?
15.
Oh, 15. I've misplaced a decimal. My apologies. $15. All right. All right, let's come over and look at resistor 2. And we only have one thing, so let's go somewhere else. Wait a minute. We have a total voltage. Oh, we don't have another voltage yet. Okay, so let's go down to number 2. And let's multiply up. And if we multiply the resistance times the current, we multiply the resistance times the current, we get the voltage. All right. So let's multiply 18 times 0.15, and what do we get?
2.7.
Say again?
2.7.
2.7 volts. Is that correct?
Yes.
Okay, and we could multiply that times the power. We'll do that in a minute, though. So we still don't have anything in our number 1 resistor, right? But now we have, I guess this is that problem I was thinking of. We have 100 volts as our total, ET, is equal to E1 plus E2. So E1, we don't know. E2, we have 2.7 volts. So I'm thinking if we subtract 2.7 volts, is that right? Only 2.7 volts?
Yes.
Wow. 100, we'll subtract 2.7 from both sides, and we'll get 100 minus 2.7 is E2, so that is 97.3. Well, let's stick this in over here. Okay. Now let's divide down. And it sure looks a little bit like 4. 97.3. Now we're going to go down. And if we look at our Pioneer wheel, we can see that E divided by I gives us a resistance. So let's divide 97.3 by 0.15, and it's going to be a bunch of resistance, right? 648.66. Continuous, right? Now we know that resistance is additive. Now's our chance to check and make sure we're not screwing up, right? So now we can add 648 plus 18, and that should add up to 666.66, does it?
Yes.
Alrighty then, so our pure functional magic is working. Also, we can multiply up to get our powers. Let's do that now. Let's multiply 2.7 times 0.15. It's going to be a very small amount.
4.05.
0. Point what?
4.05 watts. 0.405.
Okay. Is that it? .045. Okay, and then let's multiply 0.15 times 97.3. Point four.
No,
What?
the
No, the bottom one.
The bottom, 18 resistor.
This is 0.45.
405. 0.405.
All right, so we can see that if we multiply 0.15 times 2.7, we get 0.405 watts. And if we multiply 0.15 amps times 97.3 volts, we'll get 14.595 watts. Now, if we add the two wattages up, this should be another opportunity to get our pure functional magic working and make sure that we have 15 watts total. And amazingly, 14.595 plus 4.405 is 15 even. I'm telling you, it's a miracle. Okay, now have we solved everything on this thing? Good.
Engineering notation, 405, is that milli? That's milli, right?
This should be 405 milliwatts, yes. Okay, any other engineering notation questions? 0.15 should be 150 milliamps. Other than that, okay, let's stop for a second while I write another problem. Alrighty now. We have a problem with 4 resistors, and I didn't write down the fact that we have a total supplied voltage of 120 volts. And we have R1 is 20 ohms. R2 has a voltage drop of 12 volts across it. R3 is 10 ohms, and R4 is 30 ohms. Alrighty then. Well, it looks like I don't have enough information because I have 3 resistances and 1 voltage. However, could I solve this problem? Well, I'm looking at it, and I don't see any place I have 2 pieces of information. I don't have anything, it seems like, where it just looks unsolvable at the moment. I'm stumped.
What's the voltage divided by the
Oh,
resistance?
well, we don't know the total resistance, so we can't do the voltage divider rule.
You gotta add the resistance from the.
Oh, well, I don't have a total resistance though.
That's how you can get it, you add them.
Oh, okay, well, let's add the resistance in. I like that. Let's take 30 and, okay, so we have RT is equal to
Oh, we don't have 3.
20
Oh, we only have 3.
plus R2.
It's not gonna work.
It's not going to work.
We don't have
Let's
3 of them.
10 plus 30. Is that gonna work? Oh, darn. Okay. Well, how about, however could I solve this? What about if we take and subtract the voltage for this resistor right here? And we know that the voltage supplied is 120 volts, and then it's E1 plus E2 plus E3 plus E4. I wonder if that would help us. 120, and this is 12, right? E2, I've got that in the wrong place. Oops, big circle. So it's 20 ohms. So E1 plus E2, I got that way too big, don't I? How about that? 120 minus 12 is 108. Is that correct? Oops. I've done it again. If I take this apart and I just look at the 3 resistor circuit, I think I'm going to have to go to the next slide. No, I'm not. I'm going to figure out a way to do this. Okay. We've got kind of a different circuit now. Now we have 108 volts. And now we have a total resistance, don't we? Somebody say yes.
Yes.
Okay, what's our total resistance? 30, 10, and 20. 50 ohms? Is that right? We've got 30, 40, 60. Okay, 60 ohms. Okay. Now, if I do that, does that give me a current?
1.8.
Now, that being said, that means that this is going to give us a current, right? Okay. 108 divided by 60.
1.8.
Thank you. Now, is that the same current that's going through this circuit? You're sure about that?
Current is constant in the series circuit.
Right, but we don't know. We didn't include that resistor, did we? Because that would change the current, wouldn't it? A third, no, because we took it out, and we took the leftover voltage and the leftover resistance, and we divided it. That's the current. Oh, I did turn it back on. Oh, darn. Okay. So my current here is going to be 1.8 amps. Okay. Now we're really unsure we're going to have the right answer, right? Everybody agree with that? I certainly hope that 108 divided by 60 is really 1.8. Because now we really need to do our pure functional magic, make sure everything came out right? Okay, well, let's multiply up and get our voltages. 1.8 times 30. Okay. And let's make sure I'm okay. So 1.8 times 30 is 54 volts. Okay, 1.8 times 10 18 volts? Okay, and we have 12 volts here, and then 1.8 times 20 is what?
36.
Thank you. Now, let's add that up. 54 plus 18 plus 12 plus 36. All right, it adds up to 120, a miracle, I tell you. All right, so somehow we stumbled into the right answer. So that's 120 volts, so we've checked to make sure. Oh, heck. So we know that this is correct. Now, let's divide down. Now, 120 divided by 1.8 would give us what?
66.66.
Okay. Now let's get our current, our resistance everywhere else. The only place we don't have it is here. 12 divided by 1.8 is what?
6.6.
Okay, so now let's add up all resistances. We have 60 plus, no, I'm sorry, we have 30 plus 10, that's 40, 50, 60 plus 6 more, 6.6 more, that's 66.66. So now we're sure that we have stumbled into the right answer somehow. Amazing, I tell you. All right, so I think that was a good exercise. Let's turn this thing back on, and we'll find the power this time. And now, 1.8, let's get our individual powers first. 54 times 1.8 is what? Okay, and 18 times by 1.8?
32.4.
And 12 times 1.8?
21.6.
And 36 times 1.8?
64.8.
Now let's add those up and find what we find. 97.2, 32.4, 21.6, and 64.8. Adding always seems to be the hardest part. 216?
Yep.
Okay. We think that's power total. Let's multiply 120 times 1.8. 216. I'm telling you, it's a miracle. Pure functional magic, at least. All right. So we've got everything. We found out everything we need to know about this thing. And there we go. All right. We have one more problem. If I do this problem, I'm going to shoot over. I already shot over my 15 minutes. Okay, never mind. All right. We have a problem we shouldn't be doing. Because number one involves a motor. Number two involves 120 volts AC. And we don't know anything about AC just yet. But if we look at it in a very simplistic way, maybe we can do this. Okay. And what this problem is talking about is voltage drop of the wires. Now, it says that the total resistance of the two wires is 0.2 ohms. So that means that each wire has 1 ohm resistance, right? Now, we've talked about that wire has a resistance no matter what. No matter how short it is or how long it is, it's going to have some resistance, right? And it's going to cause some voltage drop. So the motor, in this case that we're talking about, is not going to get 120 volts exactly, is it? What the problem is saying is how can we calculate the voltage drop? We treat the wires as a resistor. We've got two resistors, They're both in series, and the total resistance is 2/10 of an ohm. So we're going to look at this as two different resistances, one going, one coming back, just because that's the way I would like to do it. Now we have a motor, and it is drawing 30 amps. I forgot to put that on here. It's drawing 30 amps. And the thing that affects voltage drop most is the cross-sectional area of the wire and the current. So the current is what we're looking at here. Now, in a series circuit, the current is always the same, right? So we're going to plug in 30 amps, right? Everybody agree with that? Okay, to get our voltage drop, we just multiply up. 0.1 times 30 is what? 3 volts, is that true? 0.1 times 30, is that 3? Why get a mole of decimal place over 1 point? So we're going to lose 3 volts here also, right?
No,
Yes.
6.15.
No, it's an ohm. It's
Oh,
supposed to be an
that's-
ohm.
0.1 ohm.
Yeah.
0.1 ohm times 30 is 3 volts drop. So what you're seeing here is this thing is 240 volts supplied and at 30 amps, and how much current is going to, how much voltage drop is going to be generated by that voltage drop. Now we know that ET is equal to E1 plus E2 plus, in this case, the voltage of the motor. So we've got 3 volts here, 3 volts here. Voltage across the motor, 240 volts. So 240 minus 6 is equal to the voltage across the motor, right? 234 volts. Oops. Now, why do you think that's important?
You can increase your output.
This motor is only getting 234 volts. Okay, what is 10% of 240? It's 24 volts, right? We're not losing anything near that. But if you lose 10% of voltage getting to the motor, you cut the motor's life in half. It will live for half what it would have before that. Now, a motor generally will live 7 or 8 years on average. And how do they come up with that average? The manufacturer takes a whole room full of motors, and they give them full voltage, let them run wide open, and then they come back in a couple of years. Literally. Okay? And sometimes in 6 months, one of the motors is dead. And sometimes another motor is dead in another year. But some of the motors are going to last 15 or 16 years. So this test takes a lot of time. And they're burning a lot of energy. But it's kind of a National Electrical Manufacturers Association standards they need to know. So the average is 7 to 8 years. So if you cut its life in half, you're doubling the cost of that motor, right? Basically. So another thing about this is how much, I want to look at one more thing. Let's take this voltage drop here and multiply this up. 30 amps times 3 volts is what? 90, thank you. And we have the same thing down here, right? So what is the total power loss to voltage drop? 180 watts? So let me explain this. Even though this is a very short piece of wire, and it's not killing the motor, how many 60-watt light bulbs are we turning on that we're not getting? 3 of them, right? You're paying to run 3 light bulbs that you're not getting to do anything. What does voltage drop do? Does it do anything? Nothing constructive, but what it does do is it heats these wires. It heats the wires. That's what voltage drop does. It's heating the wire. Now, do you want to pay for a lot of wire heating? As little as possible, right? And the things that can, well, we'll talk about that next semester and how we can control voltage drop and things like that. Whole different Oprah. All right. I think that's